All right, welcome everybody to our first live stream for PHYS 251RI, Computational Research Methods in Physics. What I'd like to do today is review some of the changes to the course now that we're on an online environment. We'll take a look over the syllabus update document that I sent. We'll go over basically what the major deadlines are. There's really one major deadline now. And then we'll just kind of talk about, any adjustments we need to make moving forward. And then we'll take a look at our topic for this week, partial differential equations. Just before we left for spring break, we were on ordinary differential equations. So this is really kind of the next step. And it's a great place for us to wrap up the semester. And we'll get a preview of our final assignment over in Jupyter Notebook. Okay, so I'm going to take a look now at the document that updates the syllabus. I'm going to paste that into the chat window so you can follow along with that if you would like to. Basically, my number one assumption is that you need to be taking care of yourself for the rest of the semester, that you need to make your health and safety, both physical and mental, emotional, etc., your top priority. I do not assume this class is your number one priority. I don't even assume it's in the top 10% of your priorities. Basically, my goal in the rest of the semester by delivering this course online is to make sure you feel like you've got your tuition's worth and feel like you have gotten what you needed out of this class. You've already learned two valuable skills, numerical integration and solving ordinary differential equations. So this is really just sort of to get you exposed to this one last useful topic. Okay. And so everything in this document, I want you to understand, is understood to be flexible, right? So nothing is written in stone. So let's see. We know that online learning has to proceed differently than in class. We can't just do the same things we would have done in class. And so I'm making a few adjustments. So we will no longer be conducting warm-up assignments. You will receive credit for the remaining warm-up assignments. I think there were like 2 or 3 left, something like that. So everybody's going to get credit for those last few warm-up assignments. Don't worry about those. Okay. Next is the weekly assignment. So typically we have an assignment due about every week. We were scheduled to have 2 more due, so we really don't have that much left in terms of material. And so what I've done is just combine those into one assignment. It's titled over here, PHYS 251RI, Final Assignment. It's available in the course folder, just like all the other assignments have been. And I believe I've emailed that link out to you as well. But that's going to be due at 10 a.m. April 20th. I've even got the link to it here in the update document. So like I said, that's going to be due April 20th, 10 a.m. That's when we would have been in final exam week. So I think that's sufficient time. Like I said, we assume everything is flexible. So if you run out of time, if you can't get a Jupyter installed until April 19th, then just let me know. The other thing we had to do was Project 3. That's going to still be delivered. It's available here. I've streamlined that a little bit, so there will hopefully be less banging of the heads against the brick walls to just make it more focused on make a slight adjustment to something and get some physics out as opposed to doing a deep dive into the coding there. That's also going to be due 10 a.m. on April 20th. So you really only have 2 things left to do in this class, and that's a low-stakes assignment, a higher-stakes project. Those are both going to be due 10 a.m. April 20th. So that way you've got the entire rest of the semester just to do those couple things. So what we'll focus on here on the live streams and in office hours is just helping you complete those 2 deliverables. Okay. If you have any other outstanding assignments, please get those to me as soon as possible. And since we are no longer face-to-face, when you ask for assistance with one of those assignments, please go ahead and email the file. Please tell me what it is that you've done so far. Tell me what it is that you think where you think your understanding is shortcoming. the more specifics you can give me on a help request, the more I can help you. And so to kind of make up for our time together in class, we're going to have two venues for learning together. One is going to be a live stream like this one. These will be each Friday at 10 a.m. over here on Let's Code Physics. If you are able to make it live, wonderful. You can ask questions during the chat. You can say hi in the chat right now if you'd like to tell me you are here. And basically, I will get the link to the stream to you as soon as I have it available, usually about 10-15 minutes before the stream starts. Or you can just head to youtube.com/letscodephysics and just look for the thing that is live now, right? I can only have one live thing at a time, so it should be pretty straightforward to find. Just look for the big red circle. Basically, during these streams, I'm going to provide you a background about the topic for the week and give you some tips on completing the assignments. You're encouraged to participate via the chat feature. So you can type out your questions. You can put you can paste in some code or something about what you want to look at. But then each of these is being recorded. These are automatically recorded on YouTube, and so they'll automatically be available to you after the fact if you are not able to make it. So like, for example, I see right now we've got 3 people currently in chat. That is not our entire class, unless you've all managed to gather around a single screen, which I hope you have not done because we need to be social distancing. So anyway, socially distancing? I don't know. Anyway, so yeah, these will be available after the fact. Basically, today we're going to talk about, oops, that's not March 18th. Today is March 20th. Oops. And I bet that's not March 25th either. That's March 27th. That's what I get for copying a document from one class to another. Basically, on March 20th, we are going to talk about partial differential equations. This is sort of the next step up from ordinary differential equations. And the next Friday, we'll talk about how we work with initial value problems. So today we're going to do partial differential equations in space, and next Friday we'll talk about partial differential equations in space and time. And then from April 1st and onward, we're going to talk about, we'll sneak in a little bit about the heat equation. That's an important application. And then we're just going to do a recap of previous topics until we all feel comfortable. The other venue you have is on each Monday and Friday at noon Eastern Time. I will send out a link via email to a Google Hangouts chat where we can talk over live feed, where we can see each other, or we can talk sort of face-to-face, voice-to-voice, however you want to put it. But like I said, I will get that link to you shortly before the start of each session. Now that's your opportunity to just ask open-ended questions. You can share your screen on Google Hangouts, so I encourage you to go ahead and have your assignments open when you get on Google Hangouts. And you can share your screen so that we can see what it is you're working on. It's very important that we ask each other specific questions and get specific feedback going forward, because we don't have that time in class to literally point to the screen and say, have you tried doing this thing? Or, oh, here's where the mistake is. I can't grab your screen, but if you share it on Google Hangouts, then we can work together there. All right, if you have questions and concerns, please contact me via email or my cell number. I will unredact that once we are no longer live on the internet. In fact, let me just go ahead and do that on the other screen here. Go Control Paste. There we go. All right, that's now unredacted. There we go. Okay, so what I'd like to take a look at today is these things we call partial differential equations and how we handle those computationally. So what I've got here is a cool little feature on Google called a Jamboard. I'm going to copy and paste the link to that in the chat. Also, by the way, if you are watching this outside of the live time, if you're watching this after the fact, you can. There is a button on the YouTube interface for you to enable the live chat or to review the live chat or replay the live chat. I forget what it's called. But you can click on that, and then everything that people post in the comments will become visible to you there. So the idea here is that we want to look at partial differential equations. So we've worked with ordinary differential equations, right? We've worked with derivatives of just a single independent variable. But with a partial differential equation, you're working with a function that is a that is dependent on two independent variables. So we're going to be working with electric potential later, and our textbook uses symbol phi for that. So I'm just going to use as soon as my marker comes up. Hold on 1 second, folks. Okay, we're fine there. Sorry, I'm having a look. Okay, there we go. I had a little bit of my Chrome had a little bit of a brain fart. There we go. All right, we're going to Control Z out of that. Okay, so anyway, let's suppose you got a function phi. For today, it's going to be an electric potential. And let's say it's a function of x and y. Meaning you imagine that you've got a box, right? And so you've got x going along one axis, y going along the other axis, and you want to know what the electric potential is inside this box, right? Maybe you've got some point charges here, maybe you've got your boundaries fixed at a certain electric potential, but you want to know what phi is at every point here. So phi is a function of two variables. Well, it turns out that phi is governed by a partial differential equation, where you take the second derivative of phi with respect to x, plus the second derivative of phi with respect to y. That has to equal, let me double check on my sign here. I'm pretty sure there needs to be a minus sign on the other side, but I would rather check than be wrong on the internet. Everybody knows that's the worst thing you can possibly do, is be wrong on the internet. So we take a negative times the charge density divided by epsilon naught. So this funny little d here, this funny little delta, that's just a symbol that indicates the partial differential equation. A partial derivative literally works the same way as an ordinary derivative. You're just explicitly stating that you're taking the derivative of phi with respect to x here and leaving y constant. In other words, when I do d phi dx, I'm only looking at changes in the x direction. I'm leaving y fixed. Same thing with this partial derivative of phi with respect to y. I'm saying that y is changing, but I'm leaving x fixed, right? So you can kind of think of it as like you're isolating a single variable. There's really no mechanical, mathematical difference between saying partial phi, partial x, and d phi dx. It's just a symbol we use to help us remember that it's a different thing that we're doing, that we are working with multiple independent variables. Excuse me. And then on this side, we've got the charge density. That's just a measure of how smeared out the charge is inside the region. So if I have a positive charge somewhere, let's see, in my textbooks, positive charges are red. So if I have a positive charge over here, then I'll have a positive row over here. And if I've got a negative charge somewhere, my textbooks, negative charges are green, then I've got a negative row somewhere. And if I have no charge somewhere, all right, let's suppose I've got a region over here where there's no charge, well, then my row is equal to 0 over there. So that's just what this piece means over here. Epsilon naught's just a constant. From here on out, we're just going to take epsilon naught equal to 1. So you just pick magical units in which epsilon naught equals 1. If you have to work in real world units, you just add it in the code. It's not really a problem. So anyway, this is a partial differential equation, meaning I can't use the same techniques I used for ordinary differential equations, right? Because these things behave differently. In fact, I don't even have time over here. And so what you have here is typically what you're going to have is what we call a boundary value problem, where you say, I know what phi is along the edges. So along this box, I've got a phi on the, let's see, that's going to be the low side. You say I've got a value up here that's going to be phi on the high side, and I've got a value over here that's going to be phi on the left side, and then I've got a phi over here that's going to be phi on the right side. There we go. All right, and basically you have to take those four pieces of information and use that to figure out what is the value of phi at every point on the inside. And it turns out this, except for very special cases, this is actually mathematically impossible to do. And so a partial differential equation with a boundary value problem is ripe for use in a it's right for use with a computational study. And so what we want to do is we want to be able to take this PDE, this partial differential equation, and turn it into what we call a difference equation. So what we'll spend this morning looking at is how we do that, how we transform this thing into a difference equation. I'm going to pause for 1 second. If anybody's got any questions so far, feel free to post those in the chat. I should also mention there's probably about a minute delay between where I am and where y'all are in the stream. So there's a little bit of a lag in the stream. I forgot to turn down the low lag setting. So I'll just pause periodically for folks to be able to catch up. Okay, so let's take a look at how we turn a partial differential equation into a difference equation. So what we have to do, we have to follow a little bit of a recipe, because remember we've got this square going on here where we are interested in the potential, in the electric potential somewhere inside here. What we're going to do is divide this up into a grid. So we're going to take our x values, and we're going to splice those up into individual marks, 1, 2, 3, 4, 5. And we're going to do the same thing with the y, 1, 2, 3, 4, 5. And so normally what you do when you've got a point somewhere in here is you label it as x comma y, right? You've been doing that since 11th, 12th grade, something like that. So you're accustomed to doing that by now. What we're going to do now is we're going to turn those into an integer label instead of a discrete variable. So what we're going to do is we're going to take x and we're going to replace it with x at a particular index I. And I'm going to be exaggerating my i's because I need my i's to look different than my j's. So for example, at 0, we're going to have x0, then we'll have x1, x2, etc., all the way up until whatever the maximum is. And so each of these is going to be separated by, you guessed it, a step size. Our textbook calls that h. You're also welcome to call that dx if you prefer. I personally prefer dx because I think of that as a delta x, but I guess that confuses people going back over to the d by dx. Oh, excuse me. Actually, our textbook calls that a. I think they switched to h later. I don't know. But anyway, point being, we have to take these x's and replace them by an integer label I. So instead of thinking of this x as an individual value, you're thinking of it as an index I. Then we got to do the same thing with y. We have to replace it with an index value, but I have to give it a different index because x and y are independent variables, right? I'm allowed to move along one axis differently than I move along the other. I have to give it a different label, so we're going to give it a label j. And so the trick to doing these problems is to really exaggerate your i's curling to the right and your j's curling to the left. Half the battle is in the handwriting, I'm afraid. And basically what that does is sets us up to be able to turn everything into one of these labels I and j. Okay, so what we can do, for example, we can take phi, right? Phi is a function of x and y, right? If you go back over here, we have phi set up as a function of x and y, right? It's got a different value at every point along here. Since phi is kind of moving along everywhere in the square, phi actually needs two indices. It needs an index I and an index j, right? So phi needs to get replaced by phi ij. So phi ij means phi at x equals xi and y equals yj. It's just a lot faster to say phi ij, right? That's a lot faster than saying phi of xi comma yj, close parentheses, right? So this is just a shorthand that's going to enable us in a little bit to get this into the code, because you can probably already tell we're going to be dealing with some arrays here, and so we're going to be able to have these two as our array indices. Then we're going to start thinking about the derivative. So I'm just going to work with the derivatives with respect to x. The derivatives with respect to y are pretty easy to get after that. So like if I take d phi dx, right, partial phi, partial x, that needs to get replaced by something, and we just have to go back and think about slope, right? So anytime you want to turn something from calculus into something the code can handle, you just have to turn a derivative back into a slope. So what we're going to do this, let's say I wanted to get the derivative at this particular point. Let's use red for this. I need to grab a point to the right and a point to the left to look at the change across that point. So I'm going to have phi at I plus 1 j, right? That's going to be a point to the right, minus phi at I minus 1 j, right? That's a point to the left. So I'm going from a point to the right to a point to the left, and I'm taking the difference. Then I need to think about the denominator, right? Because slope is rise over run. Well, my rise is the change in phi. My run is the change in x. We already called that something. We already called that h. Except really I've gone 2 steps, right? I've gone from here to here, and I've gone from here to here. That's actually 2 times h. So I need to make this a 2h in the bottom. There's other combinations you can do. Like, for example, you could leave off this minus 1 here and just go from I plus 1 to I and divide by h, because you've only taken 1 step. You could go from I to I minus 1. It's all an approximation anyway. This is just kind of one of the better options, because this one's nice and symmetric across the point, as opposed to favoring the right side over the left side. Similarly, when it comes time to do the derivative with respect to y, instead of I plus 1 and j, you just have I and j plus 1. And instead of I minus 1 and j, you have I and j minus 1, because at that point, you want a derivative with respect to y, you have to go 1 point above and 1 point below. Again, that's going to get you 2h on the bottom. It's just a question of whether you're going in the vertical direction or whether you're going in the horizontal direction, right? So that just determines which index gets changed, I plus I or j, right? And it really kind of reinforces this notion of partial derivatives, because you're only ever changing I or you're changing j. You're never changing both in the same term. All right, so that's a first derivative. How about a second derivative? Let's try second derivative of phi with respect to x, right? This one gets slightly more, I hate to say complicated, it gets a little bit more lengthy, right? Because you think about it, you have to apply this twice, right? If you end up applying this twice, you get this interesting little FOIL thing. I don't have the space to derive it here, but basically you take phi, there we go. Basically you take phi to the right, so phi I plus 1, leave j alone, plus phi to the right, to the left, I minus 1, leave j alone. And you subtract from that 2 times phi, I'm going to run out of room here, I j. Let me get my I and j dotted. So basically what you're doing, you're taking your point to the left and your point to the right. You're adding those together, right? Because you would subtract this one from the right minus this one from the left. That becomes a minus, minus, blah, 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 becomes a plus. And you're taking minus 2 times phi ij, right? Then you're going to divide that by, I need the step size squared, right? Because this thing is getting squared down here. I need units of length squared on the bottom. So this is going to get divided by h squared. And then again, to get second derivative phi with respect to y, you just do the same thing, but you're changing j instead of I, right? So let's try that out with Laplace's equation. Excuse me, Poisson's equation. Laplace's equation is a simpler case of Poisson's equation. So let's try this with Poisson's equation. I'll need to refer back to this later, so I'll come back to that when we need it. So Poisson's equation is second derivative of x with, excuse me, not second derivative of x, goodness. Second derivative of phi with respect to x plus second derivative of phi with respect to y, right? It's the Laplacian, going to equal negative rho, and again, we're just going to set epsilon not equal to 1 just to make life easier on ourselves. Okay, so if we go back to here, to our little recipe, this is the recipe you follow every single time. So second derivative gets replaced by this thing. Okay, so for this piece here, let me get a little color coding here. So for this piece, we're going to have phi at I plus 1j plus phi at I minus 1j dot dot minus 2 phi at ij all over h squared. Then we need to do the same thing for second derivative with respect to y. So now the green term is going to be plus, it's going to look very similar, right? Phi I j minus, or excuse me, j plus 1 plus phi I j minus 1, right? Minus 2 phi ij, all divided by h squared, right? So here I'm changing the i's, I plus 1, I minus 1, leave j alone, leave j alone. Here I'm changing the j's, j plus 1, j minus 1, leave the I alone, leave the I alone. And you notice they look very similar, right? The only difference is where the plus 1 and minus 1 goes, because here you're going a point to the right, a point to the left, a point above, a point below. And it kind of makes sense, right? You want to get the second derivative. The second derivative is a measure of the concavity, of the curviness of this thing. Well, the way you get that is by looking at the points immediately around it. You look at the point above, the point to the right, the point to the left, the point above, and the point below. And they're all over h squared, so I can actually combine these. We'll do that on the next slide. Then I need to just change the right-hand side. So this whole thing is going to equal negative rho. Now, rho is also a function of x and y, right? Because my charge density can change depending on where I am. So this needs to also become an ij, right? Any function of x and y just becomes an ij. So this is saying rho at that particular coordinate gives you how much phi changes by at the various points around it. And it kind of makes sense, right? If I put a positive charge somewhere, that's going to change the potential around that particular point. It's really, this doesn't contain any new information compared to the calculus version. It's simply writing it in a discrete version, simply talking about it point by point instead of as a function. And you say, okay, that's wonderful. I still don't see how this is going to go into the code, right? Because the thing we're interested in solving for is phi. And I've got 1, 2, 3, 4, 5 different phi's on here, right? So how in the world am I supposed to get phi out of this? Well, the answer is we're going to take this equation and we're going to solve for phi I j. Right? Because I can combine these, right? I can combine this term and this term and then move everybody else over to the side with rho, right? Let me show you how this works. The first thing we're going to do is multiply both sides by h squared, right? So we're going to end up with an h, I can draw a better h than that, an h squared times rho I j, right? Negative rho I j, excuse me. Negative. Yeah, it still has a minus sign on it. Yep. Then what we got to do is move. So now you can imagine these h squareds are gone. Well, now I just have to subtract all this other stuff to the other side. So I'll have a, let's see, I'm going to have 4 phi's. I'm going to have a phi, and I'm only moving over the ones that have plus 1 or minus 1, right? So I'm going to leave the phi ij's alone. So I'm going to have a phi I plus 1j, a phi I minus 1j, a phi ij minus 1, a phi ij plus 1. I flipped the order there, but it doesn't matter because I'm just subtracting all of them, right? So I'm taking this one minus this, or negative this one minus this one minus this one minus this one minus this thing. right? Because I've taken all of these things that aren't circled and swept them over to the other side. What does that leave me with? Leave me with a negative 2 phi ij and a negative 2 phi ij. So I'll have this whole thing equals negative 2 phi ij. Do you notice what all these folks have in common? They've all got a minus sign. And you know by now, if everybody in the equation has a minus sign, then nobody needs a minus sign. Excuse me, that's not a 2 there, is it? That should be a 4. Because I have two 2's, right? I got a 2ij and a 2ij. 2 plus 2 still equals 4, I think. I don't think they've changed the rules on that in the 2 weeks that I've been gone from campus. There we go, 4ij. And so really all I got to do is take this side of the equation and divide it by 4. Right? So my phi ij, can I write this in one line? I don't know if I can get this in one line. My phi ij is just going to be a quarter times this thing. And what you notice about this thing, this is just the average or the total of all the values around that point. It kind of makes sense, right? The value at this point needs to be the average of all the points around it. That's kind of a cool result. I take phi to the right, phi plus 1j, plus phi to the left, phi I minus 1j, plus phi to the below, j minus 1, plus phi above, phi I j plus 1. And then we add to that, oops, I don't want to close parentheses yet. We add to that h squared rho I j. And that's it. That's how I get phi at any point ij. And you say, but Dr. Lane, we don't know what any of these phi's are, right? Because in order for me to get the phi's, I have to know the phi's. It looks like we haven't made any progress, right? Well, the answer is a technique called over-relaxation. The idea of over-relaxation is that you start with a guess for phi. And I know that sounds horrifically inaccurate. Students always balk when I say we're going to start with a guess. But basically, you start with a guess for phi. You plug that guess into these values. And what's going to happen is this equation, working together with the row here, is going to correct that guess. It's going to make that guess more accurate if you feed it in through here. So you're going to get a more accurate version here. So then what do? Well, you take this one, you plug it into these. You take this set, plug it into your set of phi's over here. You get a better guess. Then you plug it back into here. It gets you a better guess. You plug it back in here. It gets you a better guess. You keep repeating this until the thing ends up looking better, until the thing stops changing. And so this is how we're going to solve Poisson's equation in our final assignment. Let me take a 60-second hydration break, and we'll get into what the assignment looks like. Okay, let's take a look at how this works out. So our goal is to use this construction here to get a progressively better guess of phi everywhere. So it's kind of like you're solving for the entire function at a time, whereas in ordinary differential equations, you hop from one point to the next. In partial differential equations, you're kind of solving the entire thing at once. It's actually kind of a cool concept. Let's take a look at how this works out in our Jupyter Notebook file, which is freezing on me. There we go. Okay, so what I'm going to do is ask you, before you start this assignment, to read section 9.1 of our textbook. It's going to go over exactly what we just went over, just in better handwriting. And it's going to walk you through, why this is of interest, etc. So here's Poisson's equation. What we're going to do is set up, and I've copied this directly out of the textbook just to make it easy. So if you want to follow along, you can either download this from our course folder, or you can look on page 409 of the textbook, example 9.1. This is the solution method presented there. So first we're going to have the number of grid squares on a side. This is the number of i's and j's we have. So we've taken our square. Let me grab my page marker here. So we've taken our square and we've divided it up into 100 lines on one side and 100 lines on the other side. So we've got a 100 by 100 grid. This is also sometimes called the mesh. Your textbook called it a grid, but it's also sometimes called a mesh. This V here, this is going to be the voltage or the potential set at the top. So up at the top, we're going to have phi equal to 1. Everywhere else, we're going to have phi equal to 0. All right, so the top is the piece that's going to have phi equal to 1. Then we have this thing called the target. This is called the target accuracy. Basically, this is how close we want the solution to get to being accurate. Because think of it this way. We start out with a guess, right? So we're going to start out with a guess that is completely wrong, right? Then we're going to modify that into a better guess. Then we're going to modify that into a better guess. Then we're going to modify that into a better guess. Eventually, though, those guesses aren't going to change much anymore. And so that's when we've reached the target accuracy there. All right, so this target is measuring how much has the guess changed by, and once it changes by less than this amount, then we're done. All right. All right, let me clear my doodling here. Let's see, and then the X-min and X-max, X-min, X-max, those are just the starting and ending values, so we're going from 0 to 100, and then our dx is just going to be, you guessed it, X-max minus X-min divided by the number of squares. So that's going to be, this is going to be the size, this is going to be our step size. So this is what we called H previously. I don't know, I like calling it dx, maybe you like calling it H better, you can change it if you want. Here we're setting up the charge density. So currently we've got 0 charge density. So we're saying, let's pretend there's no charge in here. The only source of potential difference is going to be that V at the top. Your assignment your job in this assignment is to change this. All right, we'll go over what that looks like in a second. Then here is where we create our arrays. So here we've got our phi. You notice it's got 2 indices. Remember, this is matching up with that phi of I and j. So you can think of this as being a matrix, right? Where you've got I going along one way and j going along the other way. So you've got all these different little entries in it, and they've each got an address in the array phi ij. Okay. This piece is a fancy way of saying that you want all of the endpoints to be set, or that you want the top to be set equal to V. So at the top here, we're going to have V, and then everywhere else we're going to have 0. How do I know it's going to be 0? Because I've used the zeros function. Zeros just means create an array. It's all zeros here. This is not stuff you necessarily have to change. You might have to change this V in the assignment. I don't remember. But, you can change that at V up above. You don't necessarily have to change that here. Then we have this thing called phi prime. You say, wait a minute, I have phi. Why do I need a phi prime? Well, this is where you store your next guess. So you can think of phi as being your current guess. And you can think of phi prime as being your next guess. All right, so prime just means different. Don't think of it as being derivative here. Just think of phi as meaning different. Okay? Let's see, I'll clear my doodling there. And then here we've got our list of values for x and y, just like we've done previously. That's going to be useful later on when we get to our function rho. Okay, here is the main part of the show. Okay, so here we've got, we're calling this thing delta. This is the maximum difference from one guess to the next. And so we're saying, well, delta is greater than target. So delta is my error, right? Delta is the amount of difference I have from one guess to the next. So if delta is bigger than target, we got to keep working. We got to keep honing in on a better solution. But if delta is less than or equal to target, then we're fine. Then we're done. We can leave the loop. So we're going to keep repeating this until the work is done, right? This is a nice generic way of telling the computer, continue until the answer is good enough. So what do we do? Well, we need to calculate the new values of the potential. That's where we've got our equation from the whiteboard, right? So let's go and compare that. So here I'm going to have the 4 phi's, right? I'm going to have phi to the right, phi to the left, phi below, and phi above. What do I have here? I've got phi to the right, phi to the left, phi above, and phi below. Phi below, not phi below. Phi below is a great store. I hope they're weathering the storm all right. Phi below. So we're taking the average of those, right? We're taking those and dividing it by 4, right? So if you have no rho, if you've got no charge density, this is really where it ends, right? This is all you need. But if you have a rho, we have to add this part on. So we need to have h squared times rho. So here I've got h squared, oh yeah, divided by 4. Here's the divided by 4 right here. Forgot about that part. So you got h squared, you got your step size squared divided by 4 times rho at I and j, right? So this is saying I want rho at x of I and y of j, because I is my x index, j is my y index. And so that gets passed up here to that function we had earlier. That's currently 0. Again, this is the piece that you'll change. And then basically we calculate delta. So delta is going to be the maximum difference between phi and phi prime. So the way this works is Python is going to search through the array called phi and the array called phi prime, and it's going to look for the difference between the two. So look for the largest difference between the two. As long as that difference is bigger than target, we're going to keep repeating. And this is a new trick I learned. I did not learn this trick until this week, that you can set up an equal sign like this to swap two things. So here it's saying phi gets replaced by phi prime, and phi prime gets replaced by phi, right? Because I need the new guess to become the old guess by the time I loop back around. I thought it was pretty cool. That's a neat way to swap things. It certainly saves a lot of space. Then we make a plot. This is not something you need to change. This will automatically take care of itself. This creates your plot. So here is our v equals 1 potential. Here is our v equals 0 potential. And here's how it fades out between those. That is a beautiful plot. That is amazingly done for only 100 by 100 points, right? Excuse me. That is pretty amazingly done, I think. And so what you can do, you can play around with this. You can change the v, for example. Let's suppose I increase the v by a factor of 5. Let's hit Control Enter to run. This takes, it doesn't take too long. It took mine maybe a minute last time to run. Assuming my computer is not crashing because I'm running too many things at once. Nope, I'm still live. Okay, I'm still good. Okay, well, we'll wait for that to spit out. I knew that was a mistake to do on the air. But what I want you to do for this assignment, I want you to take this whole thing and copy and paste it into this space below. I want you to be able to have this as a reference. So copy and paste this below. And I want you to set it up so that there are 2 square charges inside the box. Do we have a result yet? Okay, I'm just going to leave that behind. I want you to set this up so that it's got 2 square charges inside the box. Here's what that's going to look like. You'll have your box here, right? I want you to set it up so that there is a square of positive charge in one corner and a square of negative charge in the other corner. And the way it'll work is that these each need to be 20 units wide. So that's going to be 20. And they need to be 20 units away from this edge, 20 units away from this edge, and I didn't draw this very well, but 20 units away from each other. So 20, 20, 20, 20, right? So this thing is going to be within one region over here. This thing is going to be within another region over here. The way to do that is using if blocks, right? So you're going to say, so you're going to have your positive region here. You're going to say if x and y are in the positive region. Now, that wording will not work. This is just pseudocode for right now. Then rho equals positive 1. Else, if x and y are in a negative region, then rho equals negative 1. Otherwise, rho is just equal to 0. So you're only going to have charge in this square and this square. So this needs to look something like if, actually I can do this better than that. Let me get my eraser up. Go. So what that needs to look like is something like if, let's say we call this x left and x right. So if x left value less than x right value, and so this is probably going to be, let's say this is for the positive charge, this is going to be 2, 4, 60, less than x right is going to be 2, 4, 6, 8. Right? And do a similar thing with y, right? So y is going to be, there's 20 there, 20 less than y less than, what is that going to be, 40? Right? So this part right here is going to be your positive region. That's what that should end up looking like. Then you should do the same thing here for the negative region. Figure out what the bounds are for that and just put in if number less than x less than y and number less than y less than number. Excuse, did I say y there? Excuse me. Number less than x less than number and number less than y less than number. Right? Then you're going to have rho equals positive 1, and then similar thing here, number less than x less than number, and number less than y less than number. The numbers will be different, right? The numbers are going to be whatever the boundaries are for these squares. And so I'm leaving that up to you to figure out what those numbers are going to be and how to put those in there. But you can do this. You can combine inequalities and say something like 1 less than x less than 3. You can put that into an if block like that. It actually works out really well. And so that's the main thing you'll have to change. I'm also asking you to set all the boundary voltages to 0. And so that's just a matter of taking this V here, this V value up here, and setting it equal to 0. That's the only other piece you have to change. Those are literally the only things you have to change. You run that, get out a pretty graph, and you submit that. Then here I'm asking you to create 4 square charges, 2 positive, 2 negative, in any location you like. You could put those at opposite corners. You could put positive, positive, negative, negative. You could put them in a diamond shape. I don't care. You put those positive charges those 2 positive, 2 negative charges anywhere you would like inside the window. So I think that'll be a pretty fun assignment. It's going to get you out some pretty beautiful graphs like we saw earlier, and like it's taking mine for, I swear it took mine a minute to run last time. It's probably, it's probably because I have my capture software running that has to run on top of everything else. So your results may vary. Let me see. That's all I have on my notes for today. I would be happy to entertain any questions in the chat. Otherwise, I will see you in office hours later today at noon, and then again Monday at noon. Thank you all so much for watching. Have a safe and healthy weekend.